Hi, this is Professor Stugard, and in this video we're going to talk about confusion matrices and how they relate to evaluating our binomial classification models. So in this video we're going to talk about a few things. First of all, we're going to kind of review how binomial classifiers work, and then we're also going to talk about how we evaluate how well our classifiers work by talking about accuracy, recall, precision, and what an F-score 1 is. So, first of all, just kind of recapping, remember our binomial classification is when we're trying to predict whether or not an individual observation is going to be part of a specific group or not part of that group. So a binomial classification means, again, there's going to be, well, two options. Our classifier is going to take a piece of data and it's going to determine whether or not it believes it belongs to a certain class or it does not. Those two binomial options. This happens all the time when we're trying to build models that, for example, like we want to determine whether or not a particular purchase is going to be fraudulent or not, or an incoming email is spam or not, right? We have those two options. Either it belongs to a group or it does not. Now, after we've trained our binomial classification model, and actually whenever we've trained any machine learning model, remember we always set aside our testing data at the end, and we're going to run our testing data through our classifier to see how it does. Now, with a binomial classifier, there's going to be, well, a couple different outcomes because it's going to predict whether it belongs or not. So we have the prediction, yes or no. And then because it's testing data, we actually know the answer. It either belongs or it doesn't. And so that means our binomial classification model, after it runs through its testing data, each piece of data is going to fall into one of four categories or four possible outcomes. There are two where the model is accurate, where it did what we wanted it to do. And that's going to be where the first one is it predicted that it does belong. And we know from the testing data that it does actually belong. So it is a true positive. It predicted it should belong. And that was a true positive prediction. The other one would be a true negative. The model predicted that it does not belong. And turns out it shouldn't belong. Those are the two times that our model is accurate. And that's how we determine the accuracy of our model. We look at the overall ratio or the proportion of those two correct predictions, the true positives and the true negatives, right? Those two quarters of our confusion matrix, where again, we're filling in the number of observations that fit into each one of those when we actually go back and evaluate how well our model did. So the formula, though, would be we take all of our true positives plus all of our true negatives, those two where we were accurate, add them together, that becomes the numerator, and then we're dividing it by all predictions, or the size of my testing data, right? And that is where we did accurate predictions from our model. But if there's two where it's accurate, then there's going to be two where there's an error. The first one we can see is that it predicts no, right? Our classifier predicts that no, it should not belong, but it turns out it should belong, which means that our classifier made a false prediction and it falsely predicted negative. The other one would be a false positive. So again, false because it made an incorrect prediction, but this time it predicted it should belong, but it turns out it should not have actually belonged. It did not belong to that group. And those are the two ones where we have an error. Now, you might actually recall from statistics or hypothesis testing that this actually shows up when we evaluate whether or not we did our hypothesis testing correct, because we could have a false positive, which is also known as a type 1 error, or a false negative, which would be a type 2 error. So this idea does go back and forth between statistics and hypothesis testing as well as machine learning, but we're going to stick with the false negatives, false positives, as we try to evaluate how well our model did. So first, let's actually take an example. We're going to take a random, well, not quite random, but I made up an example where we had a test data set with 260 observations. I ran it through my trained model, and these were the results of the confusion matrix that I got at the end. And I want to see how I did. So let's start off with the accuracy. Remember, those are going to be the top two where it's the true positives and the true negatives. And so if I take a look at this one, all right, well, I have one true positive, 250 true negatives. So if I add those together, that's 251 out of the 260 total observations, or the 260 total test cases that I ran through. And if I just find that ratio, that is 0.965, or an accuracy of 96.5%. it seems like my model here is actually very, very accurate, which is probably good, right? Except, well, let's look a little bit deeper, because if I look at just the ones that were yes, my testing data, I know that out of my testing data, well, it predicted one true positive. That's good. But then, well, I also had 9 that it did not predict correctly. I had 9 false negatives. Well, that can't be very good. That's way more frowny face than happy face. So, wait, what's going on if I had that sort of accuracy? Well, this is where we want to consider the actual total of our observations in that testing data to begin with. And again, the testing data should match the training data as well. So we should be able to look at this before we even start training our model, so we have an idea. Again, understanding the data first is always a great first step. But in this case, out of those 260, only 10 of those were actual yeses and 250 were no's, which means that actually out of my testing data, only about 3.8% were actually yeses, they did belong, and a whopping 96.2 did not belong to begin with. That means that this is what's called unbalanced data. That means it is much more unlikely that we end up in that yes category, that it is part of that group, than not. And that means we're going to actually need to use some different evaluation metrics. So, what are those evaluation metrics? Well, first of all, we have recall. Recall is going to be a measure of how good the model is at predicting those yeses. So it's going to look at that row that we just talked about. So it's going to be the true positives, right? Those are the ones that are predicted correctly, but then it's going to be divided by the true positives and the false negatives, or again, that row. So in this case, row is also going to be referred to as sometimes our true positive rate, right? Is the rate of true positives, or the sensitivity. And you'll hear that term hopefully a lot coming up in different contexts, but sensitivity is very important when we come to train different types of models, and we'll talk more about that in just a little bit. But let's actually go ahead and calculate this. So my recall for this is, well, I had 1 true positive, but there were 10 that were actually yeses. So 1 out of 10 is only 0.1. My recall is 0.1, and that's not very good. So accuracy, recall, we're going to talk about precision and F1. They all are on a scale from 0 to 1, just like probabilities, right? What is the probability here? And yeah, 0.1 is not good. We only got 10% of the yeses correctly identified. But that's not the only way that we can evaluate how well our model did. We can also look at the predictions, right? The ones that it predicted yes. Did it make any mistakes when it predicted yes? And if I look at this one, it predicted yes once when it was supposed to be yes. That's good. And it actually did not predict yes when it was supposed to be no. So there were no false positives here. And that might be good as well. This measure, again, if we look at the totals, because again, we should fill in all the totals here, even though our typical confusion matrix is not going to have these totals, we can look at it anyway. This is a measure of precision. This measures how good the model's yes predictions are. So when the model predicts yes, right, that column, how well does it do once it predicts yes? And so it's going to be our true positives divided by all the true positives and the false positives as well. Now, this sometimes is also referred to as the positive prediction value, but again, we're just going to call this one precision. So if I actually calculate this here, my precision, well, my true positives is 1. Out of how many times did it predict yes? Well, 1. So 1 out of 1 were predicted correctly. So I actually ended up with a precision score of 1, or 100%. It was 100% accurate. Every time my model predicted a yes, it was a yes. So that's actually pretty good, right? That seems like something that's really good. So precision and recall are going to be important with these unbalanced data sets, and it's also going to depend on really how we want to optimize our binomial classifier. Do I want to make sure all the yeses that it predicts are actually yeses? Or do I want to make sure that we're catching every single yes? And those are two very different things that we need to consider. So high precision. right? When we have a high precision, this is good if false positives are a bad thing, right? If it's really bad that I have a false positive, I want high precision. That means it's better if we miss a yes than it is to accidentally classify a no as a yes. And we'll talk about some scenarios to hopefully drill this down a little bit more, but the opposite of this would be high recall. High recall is when false negatives are a bad thing. That means it's better to answer yes, even if it's going to be a mistake. It's just better to catch every yes. That's high recall. And notice, when I say high precision, I say, oh, we're looking at the false positive. So high precision means we're looking at an error, and high recall means we're looking at false negatives. So we're also looking at an error. So again, when we're considering whether I want to optimize for high precision or high recall, it's going to involve looking at what the mistakes would mean in context. So let's look at two examples. Which one would be preferred, high precision or high recall? Example 1, pregnancy testing. All right. So again, like I said, let's look at what would happen if there's a mistake in the pregnancy testing. So if I give a false positive, that means someone is going to think that they are pregnant when they are not. And from my experience, that is very emotionally damaging if you think you're pregnant and then you find out you're not. A false negative would mean it just takes someone a little bit longer to realize that they're pregnant. And again, you're probably going to eventually realize that you're pregnant. You're going to miss your period. You'll start getting bigger. You'll have morning sickness. There's a lot of other symptoms, and you might realize you're pregnant just a little bit later. But typically, that's not a bad thing. Now, of course, there's probably fringe cases where, oh, someone thinks they're not pregnant, so they smoked crack and damaged their baby, but like we don't consider the fringe cases, right? Think about the population as a whole, right? We have to make some generalizations here. So which of these would be worse? Is it worse to tell someone they're pregnant when they're not? Or would it be worse to tell someone they're not pregnant, but they are? Which type of error is worse? And then which type of error is better? And hopefully we see here that high precision is going to be preferred here. We would rather not have any false positives and give people false hope, as opposed to, all right, it takes someone a little bit longer, right? In this case, having a false positive is worse than a false negative, so high precision would be preferred. Example 2, what about fraud detection? What about we have a purchase, it runs through. A false positive means that you tried to make a legitimate transaction and that it is flagged and it is stopped. Now, this is annoying. I've been out of state and tried to pay for dinner with my credit card and it got flagged by my credit card company. And I had to answer a phone call with an automated bot or, answer an email and they'd say, yeah, no, it is me trying to do this. And it was kind of annoying for sure. But a false negative, if it misses this fraud detection, that means that fraudulent transaction is going to be allowed. Someone's going to spend my money without my authority. And that is really, really bad. So a false positive would be annoying, but not the end of the world. A false negative, that's a much bigger problem. So if the false negative is the bigger problem, if that's what we want to avoid, that means we want high recall. All right. So again, it might take a little while to get these, figure out which one's which. Right? We can think about other examples as well. For example, if you're testing for terminal brain cancer, would it be better to have a false positive to tell someone that they have terminal brain cancer when they don't, and they go home depressed and sell all their belongings, and then you find out that, oh yeah, you don't have brain cancer? Or would it be worse to have a false negative where you tell someone, oh, I'm sorry, you don't have terminal brain cancer, but that seems like something you'd kind of figure out just a little bit later on? Which one would be better? Well, that's a big point of this video, right? That's what you want to review. There are other evaluation metrics as well. So again, besides accuracy, recall and precision are the two other big ones. We could also look at the false positive rate. So this is all the false positives divided by the false positives and the true negatives, right? Wherever the answer should have been no. This is also, again, going to be the probability of a type 1 error, sometimes called alpha when we talk about hypothesis testing. We also have a false negative rate. This is all of our false negatives divided by the false negatives and the true positives. So this is, again, the false negatives over everything that should have been yes. This is a type 2 error. So again, this false negative rate would be the probability of a type 2 error, sometimes referred to as beta in statistics testing. And then we could also look at the true negative rate. So the true negative rate, this actually does show up in a bunch of contexts, especially when we talk about how we want to train our model in terms of sensitivity versus specificity. And so our true negative rate is the true negatives divided by the true negatives plus the false positives. And again, this comes up a lot in medical testing, which one is more important, right? And so sensitivity and specificity actually kind of are sort of opposites of each other. And when we model sometimes our predictions, we look at those as kind of the X and Y axis of our actual evaluations if we've done cross-validation and a whole bunch of other fun stuff. But that's outside the scope of this video, so we'll talk about that later. Now, what we do want to talk about, and again, if we think about that last example, we did have precision and we had recall, and one was good and one was bad. So is there a way to take those together? Because we had one that was really bad and one that was really good, and we had our accuracy was just really good. Well, our F1 score is how we can combine precision and recall into one score that lets us kind of weight both of them somewhat equally. So the F1 score is the harmonic mean. And there's lots of different means. We have our arithmetic mean, which is just where you add two numbers and then divide by 2, right? That's the typical kind of mean. When we talk about mean, that's usually what we're talking about is the arithmetic mean. There's also the geometric mean. This is where you multiply two values and then take their square root. That's also a valid mean. The harmonic mean is good when we have positive ratios. So again, harmonic, if you're familiar with the harmonic series or the harmonic sequence, that's always when we have 1 over a number, 1 over a number bigger than 1, which means we have like fractions. And so the harmonic mean is a good way of actually trying to find the average of these ratios, where if one is really bad, it will help outweigh it. And so this is the formula for the harmonic mean. Again, this is going to be calculated for you every time you look at your evaluation metrics when you're actually going and looking to see how well your model did. But the way it works, it multiplies the two values, then divides by the sum of those two values, and then multiplies that whole thing by 2. And again, the F1 is really good because it combines precision and recall together, and will be a great way to kind of just see immediately, oh wait, something's not really right, and then can I tweak this to get that F1 score up while not sacrificing one or the other. So our evaluation metrics that we're going to be concerned about. So first of all was the accuracy, and from our example, we saw that we had a really high accuracy of 0.965. Our recall, which was how well we did at catching all the yeses, that was only 0.1, that's not really good. We had our precision, which was how many of our yes predictions were correct, and we had 100%. We did great on that one. And now we have our F1 score as well. And so again, we can calculate our F1 score, just plug in the 0.1, we plug in the 1, we evaluate that, and we get an F1 score of 0.182, which is not very good. That's not a great score. Again, it goes from 0 to 1, 0 being the worst, 1 being the best. We can see here that, again, because our recall was so low, we missed so many of those true yeses and classified them as no's by accident, that it really dragged our F1 score way, way down. All right, so can you answer the following questions? Number 1, the procedural part. What are those formulas for precision, recall, and F1? How do I look at a confusion matrix and find those particular values? Number 2, when would our F1 score be preferred as the evaluation metric over accuracy? And again, that also kind of means when would precision and recall be preferred as well? And then one last example. We have drones, and they are commonly used to detect leaks in natural gas pipelines or oil pipelines around the world. The drones fly along the pipeline, taking images of the pipeline as it travels, and it's a machine learning algorithm that analyzes the images that it collects. If an image is flagged, that means that a leak is detected by that algorithm, and then a human technician, is then alerted, who can review the images and then send out a team to investigate that potential link. So when we build that machine learning model to look for leaks in our pipelines, which evaluation metric should we try to optimize? Do we want high accuracy? Do we want high precision? Or do we want high recall? Which of those would be the most important in that context? So think about that. Hopefully we have a good answer for that. And that is going to wrap it up. So, as always, please, please, please take care of yourselves.